Statistics Lesson 4.3, Complements, Conditional Probability, and Bayes' Theorem. Compute the probability of at least one occurrence of an event, A, and apply the multiplication rule by computing the probability of some event, given that some other event has already occurred. So those are the objectives. Complement the probability of at least one. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. The complement of getting at least one particular event is that you get no occurrence of that event So let's see here. If we were write it, probability of, and we'll say R is greater than or equal to 1. And here would be the probability of 0, okay? Probability at least one occurrence of event A equals 1 minus the probability no occurrence of event A. As an example, a study by Square Trade found that 6% of damaged iPads were damaged by bags or backpacks. If 20 damaged iPads are randomly selected, find the probability of it getting at least one that was damaged in a bag or backpack. So let's let A equal at least one of the 20 damaged iPads. In a bag or backpack. So identify the event that is a complement of A. So let A complement not getting at least one of 20 damaged in a bag or backpack among the 20. Or you might say all 20 iPads damaged in a way other than bag or backpack. Okay. So we want to find the probability of the complement by evaluating the probability of A complement. So how are we going to go about doing this? Well, let's see. It said 6%, right? It said 6% of damaged iPads were damaged by backpack. So 1 minus 0.06 is 0.94. Okay? So the probability, let me get a little bit more room here. The probability, I'm messing up here. The probability of the complement of A is going to be 0.94 times, and you could do that 20 times, or you could just say 0.94 to the 20th power. Okay, and let's see, calculator, 0.94 carry to the 20th power, and it's going to be 0.290. 0.290. Now, find the probability of A by evaluating. The probability of A is going to be 1 minus probability of A complement which is 1 minus 0.29, which is 0.71. 710. Okay? For a group of 20 damaged iPads, there is a 0.710 probability of getting at least one iPad damaged in a bag or a backpack. The probability is not very high, so to be reasonably sure of getting at least one iPad damaged in a backpack, more than 20 damaged iPads should be used. Okay? Conditional probability. Consider the principle that the probability of an event is often affected by knowledge that some other event has occurred. I believe in the book it talks about the average person, there's a 1 in 12,000 chance of hitting a hole in one. But if you find out that person is a professional golfer, it changes to 1 in 2,375. So conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. The probability of B given A, the conditional probability of event B occurring given that event A has already occurred. Conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that event B will occur. So the probability of B given A equals the probability of A and B divided by the probability of A. All right, so let's see here. We got this table and we want to find P, the probability of a positive test result given the subject uses drugs. Okay, a positive test result given that the subject uses drugs. Well, if we take the intuitive approach, well, what's the positive test result? All right, that would be 45. Okay, so we'd have 45 over, and then the subject uses drugs, so that would be 45 over 50, which is 0.900. Okay. If you take the formal approach, and let's do the formal up here, the formal, you would say, okay, positive test results, we would have 45 over 555 divided by, and then subject uses drugs, that would be 50 over 555. Okay, so that equals 45 over 555 times, and this 555 divided by 50, invert and multiply. So these cancel out, and then you still end up with 45 over 50, which is 0.9. Okay, so the intuitive approach here, and then up here the formal. Now, what about finding the probability the subject uses drugs given they've had a tested or a positive test result? Now, that looks a lot like this first one, okay? But it is slightly different, okay? So the subject uses drugs, okay? Subject uses drugs, okay, 45 again. Now, positive test results. How many positive? 70. Okay, so that's slightly different. And that turns out to be 0.643. Okay. The first result, 0.900, indicates that a subject who uses drugs has 0.9 probability of getting a positive test result. The second result, probability subject uses drugs, given positive test results, is 0.643, indicates that for a subject who gets a positive test result, there is a 0.643 probability that this subject actually uses drugs. And sometimes when, how do I say this? Sometimes when people get these mixed up, it's called the confusion of the inverse. And it's a quite common problem, but we're not going to spend a whole lot of time on that in this class. Okay. An example of that is the probability that it is dark, given it is midnight. The probability it is dark, given it is midnight, is 1. Okay, unless you happen to live in Alaska or something like that. But here in Tennessee, it is 1. Now, the probability that it is midnight, given it is dark, okay, that's a little bit different. That's not 1, okay? Why? Well, I don't know about y'all, but I think last night it got dark at 5:45, and it was dark till like 7:10 or something like that. So that would be quite cumbersome. That would be quite cumbersome to calculate. So you could say that the probability is dark, given it is midnight, is not equal to the probability that it is midnight, given it is dark. Okay, they're not equal. Same as up here. These two results were not equal. All right. Bayes' theorem. Now, to explain Bayes' theorem, first I'm going to do one that is a little bit like we've been doing, okay? Assume cancer has a 1% prevalence rate, meaning that 1% of the population has cancer. Denoting the event of having cancer by C, and that's what I got here. Let's see here. C, so the probability of cancer is 0.01 for a subject randomly selected from the population. This result is included with the following performance characteristics of the test for cancer, and this is based on probabilistic reasoning in clinical medicine. All right, so the probability of cancer is 0.01. The false positive rate is 10%. That is, probability of a positive test result given that cancer is not present. Okay, so false positive. That's probability of positive test result given no cancer. No cancer. All right. And then the true positive rate is 80%, and that would be the probability of positive test result given has cancer. All right. Now, what we want to find is cancer given a positive test result. Now, believe it or not, we can use this information to fill out this table. And what we're going to do is let's take a look at this. We're going to say we have 1,000 patients, right? It's actually, it's based on more. But we're going to assume we have 1,000 subjects. With a 1% prevalence rate, that means 10 of the subjects are expected to have cancer. So this total over here is going to be 10. The sum of the entries in the first row, in this first row here, is going to be 10. All right. The other 990 subjects, okay, because 10 plus 990 is 1,000, do not have cancer. So the sum of this row here is going to be 990. Among the 990 subjects without cancer, 10% can get positive results. So the false positive rate is 10%. So 10, that's going to give me 99. We're going to put it right here, 99, okay, 99. Which means that's going to be 891, okay, all right. Among the 10 subjects who have cancer in the first row, the true positive rate is 80%. So positive test rate, that's going to be 8, right? So that's going to make that 2. All right. Now, if we add this, we get 107. All right. And if we add that, we get 893. Okay. Now we can use this to find cancer much easier. We can find that. The probability of having cancer, that's going to be 8, over a positive test result, that's going to be 107. 107. And that works out to about 0.0748. Okay, so the probability of having cancer given a positive test result is only 7%. Okay, which is kind of good news if you you get one of those reports. Okay, now that's how to do it. There's actually a slightly easier way. Okay, than filling all this out, but you might prefer to do it this way here. Okay, we're going to do Bayes' theorem. Okay, Bayes' theorem, the probability of A given B. So we're going to say the probability of A is cancer. All right, and the probability of B given A is going to be positive, probability of positive test result given cancer. Okay, kind of running out of room, so I just did a little thing. All right, so here we go. So the probability of cancer given positive test. All right, and then so let's see here. That's going to equal. So the probability of A. Well, we already got that off the other thing. That was 0.01 times positive. Positive and that rate was 0.80. Okay. Now let's divide that by the probability of A. That's going to be 0.01 times 0.80 plus, and then the inverse or the complement, and that's going to be 0.99 times the probability of B given the complement of, or probability of positive given the complement of cancer. Okay, and that's going to be 0.10. Okay, and let's try that. Let's put that in the calculator. So we got control divide 0.1 times 0.8 over, in open parentheses, 0.8 0.01 times 0.88. I got to go up here and put a 0 in there. I'm about to mess that up. Plus, open parentheses, 0.99 times 0.1, enter, and that's, wow, we got the same thing. 0.074, or yeah, 0.07, and then, let's see here, what did I, 748, and then 0.74, and then what was the last one? 7.6, or rounded up to 8, okay? So maybe it would help if probability of cancer times the probability of positive result given cancer divided by probability of cancer times probability of positive given cancer, and then plus probability of the inverse of cancer, or not the converse, the complement times the probability of positive given the complement of cancer, okay? And there we go. It takes a little bit. You got to practice a little bit, okay? It's when we do a couple in class, you'll understand. Prior probability. An initial probability value obtained originally, an initial probability value originally obtained before any additional information is obtained. So like the probability of cancer. Posterior probability, a probability value that has been revised by using additional information that is later obtained, such as finding out that the guy's a pro golfer. All right, good job, folks. We'll see you in class tomorrow, and we'll work on that Bayes theorem some. You have a good evening.